Hey guys, this is the notes for 21.5 through 21.7. And there are two major concepts we want to talk about. One that's very, very significant. It's going to kind of drive the rest of the chapter. But we're going to start out with a little bit of an understanding. Whenever we move magnets and wire, electrical wire, around each other, okay, we have the ability to induce a current or an electric flow of electricity. This is commonly referred to as Faraday's law. So if I think about, I've got this loop of wire, okay, a whole bunch of loops, right? Maybe it goes off this way. If I were to take a magnet, okay, with a north and a south pole to it, and I were to insert it into the loop of wires, right? I'm going to go right through the middle of it, kind of like, and if I were to push that in there, while it's in the process of moving, okay, while there is a velocity, okay, to the movement of the magnet relative to the copper wire, okay, there's going to be an induced EMF, electromotive force, or more commonly we refer to it as a voltage. There will be an induced voltage. Now it's really important that we understand there has to be motion relative to one another. And so if I pulled that magnet out rapidly, I would induce again a current. If you've ever had a flashlight that's rechargeable by shaking that flashlight, that would be an example of moving a magnet through a bunch of loops of copper wire and producing an EMF. Now if we want to know what is the most that we can produce, is it's going to slow down, and as we make that rotation happen, there's going to be a point at which it's at its best case scenario. We need to, for instance, the motion needs to be perpendicular to the spool of wire, the loops of wire. If the loops of wire aren't perpendicular to the motion, you're going to get less produced EMF. And so if we want the peak EMF, you could use voltage here, but I'm going to use an E for EMF. The peak EMF that we're looking at will be determined by the number of loops. Okay, so we're going to take the number of loops. The more loops you've got, the better. Times the magnetic field that you're dealing with. How strong is this magnetic field that's being produced by our magnet? Times the rotational speed, omega, times the area that it travels through. Now, the model I showed you to start talking about induced current has more to do with something called the flux, and then we're not going to spend a lot of time right now talking about that. We're going to talk about specifically motors or generators. And so forget this idea of the wire being stagnant and sitting still and the magnet moving. Let's instead imagine that we had a magnetic field, okay? And in that magnetic field, so I've got my magnetic field pointing into the board. Inside that magnetic field, I have a whole bunch of loops of wire. They're wound tightly together, and at some point it comes out. If I were to give this a twist, okay, in that magnetic field, that twist would create electrical flow through the wire. It would induce a current of some type, one way or the other, and that would because there's an induced voltage, okay, potential difference. So that induced current, if we want to understand a little bit more about it, well, it's going to depend on how many loops of wire are we talking about, how strong is this magnetic field, that's going into the board. The omega is its rotational speed, and remember, this has to be measured in radians per second. How fast is this thing spinning when it spins? And then, of course, the area. The bigger this circle is, the better. But let's remember, if you make a big circle, it's going to have more torque on it. It's going to be heavier. It's going to be a lot of things that we may not want. So there are always trade-offs in terms of producing or inducing a current. All right, so there's our basic initial idea that we can induce a current by changing the magnetic field. It's really or the magnetic field that goes through the wire. It's really important we understand that it has to be changing. If it's stagnant, then we don't induce a current, and that's not great. So let's look at an example of how this can be applied in something called a transformer. This transformer is the backbone of our electrical grid. Without transformers, AC power would not have been adopted, and we couldn't have the system that we have now. The way a transformer works, we're going to have an iron core, something that's easily magnetized, okay? Make it a rectangle like a washer, it could be round, but we're going to take this wire and we're going to wrap it around here, okay? I'm going to hook this up to some sort of an AC power supply. That's the symbol for an AC power supply. Let's say that over here I have 5 turns or 5 loops around this core. As I send the current through the wire, it's going to create a magnetic field in this washer, this core. So let's say the magnetic field starts out pointed this way. Okay. While the magnetic field is getting stronger in this direction, if I have a loop of wire over here, let's say that it's got 10 loops, okay, so 10 turns on this side. While the magnetic field is building up, it is going to, because that magnetic field goes right through the loop of wires, it's going to induce a current. Okay, it's going to induce a current to flow out down that wire. Now what's important to understand is that if we were to use a DC power supply to do this, okay, because the current in the initial loop, what we call the primary coil, is constant, the magnetic field would be constant. And because the magnetic field's constant, it wouldn't induce a current in our second side. However, if we use AC, the magnetic field will constantly be changing. It'll be building up clockwise and then switching and building up counterclockwise, back and forth. So the magnetism in this core is going to constantly be changing its direction and its size. That change is what allows us to induce a current and a voltage on what we call the secondary coil and produce some sort of voltage difference between these two terminals here and here. Okay? If it was constant DC power, there would be no induced current. That's really important. So let's say that we had 3 volts being supplied. If we have twice as many turns coming out, then the voltage coming out would be twice as big. So we can step the voltage up. We call this a step-up transformer. If we were to go with less loops on the secondary side or the second side, we would see a step-down transformer as we would drop in voltage. There are all kinds of devices like your phone, your computer, that need a different voltage than is supplied by the power outlet in the wall. We also have things where we talk about AC-DC transformation because we can't use an AC power supply to charge a DC battery. We have to transform it back to DC in order for it to charge a device like that. So, at the end of the day, there's a couple of things that we need to understand. First, the power that comes into the circuit, into the transformer, is equal to the power that comes out. That is to say that the current times the voltage coming into the transformer will equal the current out times the voltage out. Now this is important because the power is being converted the same, which it's telling us that there's no energy change here. Because the power is being held constant, okay, if we can drop the current low enough, we can save the energy losses that normally happen in DC power transformation. So in an AC circuit or AC grid that we live in, we step the voltage way high, which forces the current to drop down. You'll notice that if I increase the voltage, the current then has to decrease because of the relationship. So what this comes down to is this final step, that the number of turns in our secondary coil divided by the number of turns in our primary coil will equal the voltage in our secondary coil divided by the voltage in our primary coil, which means if we double the number of turns, we're going to double the voltage, and so on. But the current is inverse related, so the primary coil would be divided by the secondary coil for the current. Now these can all be flipped upside down to make it easier to solve, It doesn't really matter which one goes on top as long as we follow this pattern. So here's the basic idea. We have a power supply station. Okay, this is the dam power supply. Okay, it's going to produce something at, say, 1200 volts. Okay, but I need to travel, in order to save energy as I transfer the power, I need to step it up. So I'm going to go through a transformer, okay, that's going to step it up. And it's going to bump it up to something like 240,000 volts, okay, much higher voltage. And then I'm going to run it on high power lines until I get close to your house. And then at a substation, okay, I'm going to start stepping it down. And I might step it down to 2400 volts. And then I'm going to keep traveling along at 2400 volts. We'll get to a smaller step down transformer. So T down, we're transforming down to 240. And that's what's going to go into your house. Now, in our wall outlets, we use 120, but there are some outlets that need 240. So we have to start with what we need for the biggest, and then we can split it off and do voltage dividers and things like that to get down to a smaller voltage. Transformers are amazing. They provide us with the ability to charge devices at any voltage that we need, simply by increasing or decreasing the number of loops of wire. They allow us to transfer energy across great distances. Without transformers and AC power, we wouldn't have the electrical grid that we have, and we certainly wouldn't live in rural areas like we do. We're too far away from the power, and so we need to be able to transfer that. All right, I hope that helps you with your homework, and good luck. We will see you guys in class.